Hello and welcome. I'm Shadow of Shadow Gaming, bringing you Programming with Shadow, episode 71. In today's lesson, we are going to be looking more into trees. So last time we did a little small binary refreshing. So now we're going to get back to trees. So the last tree we looked at was an AVL tree. Before that, we looked at a binary search tree. So we're going to look at another extension of a binary search tree, a red-black tree. And this will be a couple lessons. I won't get it done in one lesson. I don't even know if we'll get through insert in this first lesson, but we'll look at this other type of tree. So an AVL tree, it was really balanced, and it was pretty strict. Or if you add something, you had to go re-implement or not implement readjust there. You had to readjust the tree, you had to do your rotations, and you wanted to get it back into the correct state. And as we've seen, sometimes you had to do, like, you might have to do multiple adjustments at a time. Delete can also get into that case. If you delete a node, you're sometimes going to have to do a lot of adjustments all at once. So, and each one of them takes some time. Red Black Tree tries to do a similar thing, but fewer times. So what it does is it trades your search time. So the whole goal with AVL trees and this was to keep this from happening. So the red black tree is going to try to keep this from happening as well, but it's not going to do it as strictly as a red black or as an AVL tree. So with an AVL tree, the thing we noticed, we always kept the height. So the height, you could only have a difference greater than or equal to, no, less than or equal to 1. So if you had a -1 on it or a 1 on either side, you had to start rebalancing. With a red black tree, it's a little looser on that. Your height can be roughly it ends up being 2 to the log. This is the binary log base 2 of n. So what you're trading, so you have a little bit slower lookup time. It's not going to be a perfect binary search tree where everything's completely balanced, probably, but it's almost as good, and you do less balancing, so you could get a little more implementation speed. So like your inserts and deletes are faster. This is used in some of the standard data structures and different things. I looked it up. I actually didn't look up anywhere in C#, but I would say C# probably uses it. Let me do a real quick Google just to see. Let's see. Well, it's searching Java and uses it for the tree map. If you've used C++, you use it in map and set. Sorted set. We have not looked at sets or sorted set, but it probably does. Sorted dictionary. So basically, the sorted structures look like they might use it a little bit. But yeah, so it's used. It's a little more used. It's used a little more frequently, as far as I could figure out. I've actually used the red black tree as well, and it's the one I've actually seen. So with AVL tree, we were concerned with height. Let me find our node. So if we remember, we went to the wrong spot. If we remember, we added height there nodes just for that. With red black tree, we're going to change that. We're not going to use height. We're going to use another property of color. And as by the name, the nodes can be either red or black. So I think when I think of that, I think of a checkerboard. If you've ever played checkers, you're you're playing on a lot of times you can do multiple bounces at a time. That's sort of what this always gave me a thought of, sort of checkerboard. So the other than that, that's pretty much, we'll see when I set up the node, that's pretty much going to be it. There is going to be one thing that's different though. Here we just care about left and right. With a red black tree, we also care about the parent. So we need to keep track of who our parent was, and we'll see why. There's 5 rules when you're doing a red black tree. I guess 6, maybe 6. So first rule, every node is red or black. So that's easy. So we give each node a color, and we can change those colors, but there's always some way of doing the root or of doing the color. Second rule is the root is always black. So the very first node always black. I'm going to be visualizing it like this. So like we'll say 10B. So rule 3. So does this one, you always treat anything that's null. So this would have 2 null, a left child and a right child that are both null. So you treat nulls as black. Here we'd have black, and then we'd have something like that. Something very, very loosely like that. So all 3 of them, so they all have a color. Root's always black, nulls are black. So next one, so next rule. So this is invalid. So you can't have 2 red nodes there touching. So I think the official rule is red nodes cannot have red children. I think it's what the rule actually says. So what you get is that this is invalid, so you would have to have red and black, I guess. So what this does is it's preventing you from having a long chain, so you don't have a lot of reds. The final one goes back to this one sort of. If we had actual values in this node here, so let's just change this. Let's make this one. Let's just copy actually. So the final rule, let's make this a 20, this one a 10. This one, let's do 30. Something like that. So every path from a node to a leaf, so here's a node to a leaf, these are both leaves, has to have the same number of black nodes. So what this gets you is the pattern that this keeps you from getting it long. This keeps you from getting it all down one side. So if we have something like this, so here the height, let's make it shorter. Let's cut it off here. So now we have a height of 4, right? So four values. The rule 4 prevents this from being all reds. So this one has to be black. So in rule 5 prevents it black from being too deep. So here we could have red, black. Now we have a problem. This one should be red, but now here the path doesn't work. So this one's all right. This one's not, however. So this one doesn't work. So we'd have to rebalance. And that rebalance gets us a height of this format. Height equals 2 log base 2 of n. And we have to do 1 plus 1. So there. This should be a sub b. How to represent sub b. It's a binary log, basically. So it won't, or it doesn't necessarily have to be a perfect search tree, but it does a pretty good job of keeping it pretty close. So here's a thing we're going to keeping. We're going to treat this as a sixth rule. Maybe I'm actually not sure it's a rule. It's how I've always seen it, but I don't think when I was looking it up, I don't think it was actually in the rules. But every node I insert is going to be a red node, so we're always going to insert red and then adjust. Let's do this 10, 20, 30 here. So these are a problem because here. Let's copy it down. So let's practice insertion. So we've inserted these and we've inserted the reds, but now there's 2 reds touching, so we're breaking one of the rules. So then we need the rebalance. So the parent color determines whether a repair is needed. So here it is because these 2 are both red. So if we have say we do something like this, so we insert 30 and it gets black, then we insert a 20, it goes over here, and we insert a 10, it goes over here, that should be red. Again, that's wrong. Wait a minute. Yeah, that's wrong because it's still 2 reds touching. So if we do it the other way, let's do, if we insert 20 first, then we get it in the better order. 20 becomes black, then we insert, say, 10. Red. 30 red. And there, that one won't need rebalance. So these 2 would both need rebalance. This one wouldn't. So the rebalance we'll do on these, let's say this one, we'll end up making it look like this. And if we remember from our AVL tree, that'll look very much like a right rotation. Let's see. We'll have some of the other rotations as well. We'll have the left-right rotation. So if we've got it into a broken structure, such as the 10R. R. So that one's violating the rule, and it's not an incorrect binary search tree. So here we'll have to do a 2-step rotation. We would do a left rotation and then a right rotation, so a LR rotation. I think that's pretty much where we want to go. We may start implementing, go ahead and start implementing for now. So let's see. I'm seeing if there's anything else we want to touch on first before I actually start implementing. I have a little table, but I don't think it tells us anything. So balance for AVL, it's strictly balanced, while red black, it's still balanced, but it can be a little more relaxed. Search, AVL's faster, red black is slightly slower. Like the order of magnitude of how much slower it is may not be all that much. Insertions, AVL does a whole lot more insertions, while red black might be, it's close enough, we can leave it for now. Delete's complex on both of them. We've seen AVL tree deleted, we expanded it quite a bit. We'll see that the same thing happens with red black tree. It's more complex to delete than to add. Let's see, and height's the same way. Or AVL tree does better at maintaining the height, while the red black tree is not hardly as good. So basically, you're trading a little bit of max search performance for a little bit more of insert and delete. So maybe in cases where you're going to be doing primarily searching, you'd want to use the AVL tree. Like maybe you'd create something once and then use it a billion times, then maybe AVL tree is the one you actually want to use. But if you're constantly adding and deleting, I think most of the time you're going to find the red black tree ends up working out better for you. So let's begin. So we have our tree node class here and our nice helpful printer class. We're not going to use those. When I did my implementation for this, I've been away on vacation for about 2 weeks, so it had been 2 weeks since the last recording, and at that point, I wasn't thinking of what I did before, and pretty much re-implemented it. So I'm just going to follow that. But I think we probably can just use some of the code we already have. So let's see. Change the look here again. Let's add a new project. We will call this console app. Let's call it red black tree visualizer. Let's not use the top level statements, and there we go. So let's grab our AVL tree visualizer, this one. I'm just going to copy and paste. We'll just grab this as is. We'll just paste it in here. Save this. Over here, let's add a new class. There we go. Red, black, tree. Class, red, black, tree. Let's also add a public class, red, black, node, and a public enum node color. And the colors can be red or black. There we go. Yeah, I believe that's what we want. So I'm going to leave these in the same class for the moment. We'll adjust that as we go. Did not want to run that. That was a mistype. So let's make this red black tree. Now everything's broken, so let's start fixing some things. So let's begin with let's make this print here. Here, we're just going to remove tree printer. Like I said, I'm not I'm going to use a, I didn't think to use my previous ones from how long it had been, so we'll just redo them here. And these may be pretty much the same thing, I think. Void, static void, print, red, black node, nullable, root, int, indent equals 0. Yeah, thinking about it, that's pretty much going to be the exact same thing. Let's just grab that. So that would have been here. Here, tree node visual, tree node printer. There we go. Yeah, that's pretty much going to be this. There's no height to worry about though, so there's no right value or left. We'll fix that. If we go back over here, let's make the node actually make sense. So here, let's do this. Let's do there. Let's grab our node. We'll do we'll pass in int value to give it a default parameterized constructor. Public int value get set equals value. Public node color get set equals node color red. So I said we'll use red as the default color. Now we need the public red black node left. Right. And we'll have to keep track of the parent as well. Just like that. All right. One more thing I'd like to do. Let's add a to string. So public override to string. String color equals color. No dot color. Let's just do black. I think black ends up being more common. I guess red should be. Return dollar. We'll do value. No, value color. There we go. So what that'll do is that'll print it like I did for my tree here. So we'll have value and then the number and or the letter of that, and there's no space. So that's how I'm going to represent them. Let's see. I think that's all I want for the node here. Yeah, let's kick that out to its own class file. I couldn't find the option. We'll kick this one out too. All right. So there we've got those. So let's see. So here, let's rename this Control RR, red, black, tree. We need a print in order and we need the root. We can grab print in order from tree printer over here. I bet it'll be very similar. Probably should have just used them, but I didn't think about how to do that. So we'll just use what I used. Yeah, it's even good as is. Let's make sure that's what I did, but I think that should be fine. Yeah, I didn't change it anymore. So yeah, we'll stop with that. There we go. So now we're set to get started with the red black tree itself. So this one, we're going to do it just like we did before. So we'll start with public red black node. So we'll have a root, and the root's nullable. We'll have an insert method, insert int value, throw new not implemented exception. So we'll have a search, and we'll have a delete. All right, so that gets us to a starting point. I actually think we're built at this point. So that sets up our implementation. So as I said, we may not actually be able to get through insertion in one lesson. We'll see how far we can get. So inserts decently complex. So let's begin. Let's make this say red, black tree visualizer. There we go. And now we should be ready. Not using logs, we can just remove them. All right. So here, let's begin with a comment. So we'll do console.writeLine. We'll do some, I think we did this before, so we'll say insert value like that. So our new node equals new red black value. And I'd rather do it the other way. So the reason I like the other way better, I don't know, but so it's a little shorter, but to me, it makes sense. I'm saying this is a node of this type and create a new one of those nodes. This one says, all right, create a new node, and it is this type. And somehow this one's clearer to me. I've wrote this one so much more, though, I tend to go for it first, and then like, I want to swap those. I like that it's shorter, though, and to me, it's a little clearer. It's like, this is what this node is, and I'm just giving it a new one of those. Either way, it's the same. This is going to do the exact same thing. You could even do it like this if you really wanted it to be long, but I don't think you're going to get any different value between the three of these. Except that one, which is wrong. There. I don't think you're going to get a lot of different value out of these. This one's shortest. This one's probably most common still. So take your pick and match whatever. If you're in a code base and someone they've preferred one, don't change. Just stick with it. If it's been inconsistent, pick your favorite. If you have a style guide that tells you to do one, also pick your favorite. I'm going to use this one for us today. So now let's do this. We'll have an insert node, new node, and fix insertion new node. So we'll do this as a two-step process. So insert node, it's going to be pretty easy, so we'll start with it. So we'll have a private void insert node. Takes the red black node. Not going to do it nullable. We'll see. I got the null. I think I got the nulls mixed up. So if we get far enough, we'll see that I may need to think about them just a little more. But let's just go ahead and start. So parent can be null, and in fact, it's going to start as null. We'll have a current, and it can be null because root can be null, so that makes sense. So now while current, not too many R's, is not null. Okay. So root can be null. If it is null, we're instantly done at that point. Else, while it's not null, then we'll do parent equals current. So there, parent's not null. So now if node.value is less than current.value, current equals current.left, and then else current equals current.right. So here we set parent to the current node, which was the first one's the root. And then we say, okay, if the node value is less than that value, we take the current node or the root node or the parent node at that point. We take their left child, otherwise the right. So we're just getting whichever one's the, wherever we're going to insert at, we're trying to find that. So eventually we get there though. Then we say, okay, so we've set the parent to the current, and we've updated the current to either the parent's left or right child. When we've finished this loop, then we're ready to add the parent to the node. So node.parent equals that parent we found. So we found which parent to add it to. Now, if that parent was null, so we have a chance that everything in here could have ended up null. Current is not null. Yeah. Yeah, okay, so the only case that parent should be null in that case is if root here was null. So I think if that case, this is only that, it only happens then. So this is the case if the root is null. So root equal node. So then we're done. So we just set the root and we're done. That makes sense. So else if node.value is less than parent.value, and parent.left equals node. So we set the, so if the parent's value, if the node value is less than the parent value, we set it on the left side. Else parent.right equals node. We set it on the right side. And at that point, we are done. So we have insert node. So that, we did it slightly differently, but if you go compare what's actually happening, I think you will find that insert here, we're doing it a lot like what we're doing over here. This is very similar insert, except we're not doing a recursion here. There's nothing recursive happening in this case. So this one's a recursive insert. This one is not. Here we're doing the while loop. We're saying, okay, we'll search and find where we want to go rather than recursing to where we want to go. So slightly different context, but we're doing pretty much the similar operation here. So fix insert's a little harder. Let's start it. So private void fix insertion. All right. So first things first, we're gonna need some helpers. So first helper we're gonna need is private static red black node nullable find grandparent of this node. So we'll use null here if it doesn't exist. So that's what we're doing. So we're saying we want to go back. If we have this, say we have this structure, the grandparent of 3 would be 11 in that case. And that's what we're trying to find. We'll see that this can be helpful even if there's not a lot of code here. It really cleans up what you're trying to do. Node.parent. That gets your parent. Parent can be null, so we want to pass that null through parent. So there is the class. So pretty simple. If we didn't do this, we could do our parent equals node.parent. Now, if parent is null, return parent, or return null, I guess would be clearer. Else, return parent.parent. So these two lines are equivalent, or this section and these lines are equivalent. I'm going to use the null coalescing operator because that's clearer to me. It says go ahead and if it's null, pass through to null, else get the parent.
That's exactly what's happening here. So we're going to do that, clear this out. And there we've got one of our helpers. If Copilot will quit helping me, Control dot, we'll make an expression body member because it's easy. So now we need two more classes, or two more helpers. So the next one we've seen before, private void rotate left, red black node x. I think we used x before. Or y equals x dot right. We need to handle the null case here, which shouldn't happen. That should not be null. So if that's fine, then we can do x dot right equals y dot left, y dot left. So here we're setting up everything. Dot parent equals x. We set the parent there. Y dot parent equals x dot parent. So if x dot parent is null, so if the parent's null, what do we want to do here? So if the parent's null, I don't know if what I did here makes sense. So I did root equals y. So I set it to the root. Let me check that one. That seems suspicious, actually. I don't remember why I did that. Did I do it for rotate the other way? I did. I did both of them. I'm going to check that real quickly. Let me okay, we are back. I hope sound came back. I'll check it when I get the recording done. Okay, so this was correct. So I was trying to remember what I did here. So we're setting the root to y. So this is the special case if no parent is found, the root's not set. So then we're setting the root here to y. And y in this case was x dot right. So whatever we passed in is right child. So this was a special case handling. For some reason, I don't remember why I did it, but what I'm doing is handling a special case. And that's if the root is null. I bet I didn't handle it and had to fix it. If you want to bet on it. So there and else. Thank you, Copilot, to go away. Let's see. I've lost one of my braces. So y dot left equals x dot parent equals y. Okay. So rotate left. So we set the right child to the left. Or I get the feeling this isn't what I did before. Here, well, let's go ahead and get the right child, and we may go check this and make this a little closer to the AVL because this doesn't feel familiar now. Like node x or y equals x dot left. F should not be null. X dot left equals y dot right. So we'll hook up the children. Parent equals x. Y dot parent equals x dot parent. So swap the places. So here, same thing, we'll handle the special case for the empty root. So if it's null, then root equals y. Else if x equals x dot parent dot right. And here we'll set parent right equal to y, else x dot parent left equal y. So whichever one needs to go there goes there, and then we'll do right equals x, and then x dot parent equals y. All right, so that should get us our helpers created. So let's see, let's go look at the AVL tree. Let's remind ourselves what we did here. Rotate right. We pass in a y. So yeah, I use different notation here. Here, let's start with rotate left. So we say y equals x dot right. So that's exactly what we do. The right child shouldn't exist. So x dot right equals left. Sort of what we do here. T2 in that case is right. X dot right. And then we have to adjust the parents. There's no parents over here to worry about. And we don't have to worry about the height. So yeah, I guess this is roughly what we were doing before. And over here, we return to the tree node. Here, we're just setting it. So something to keep in mind. So apparently how I thought to do the AVL tree is not how I thought to do the red-black tree. So that, I think this will work though. So that sets us up to actually do the fix insertion. I think we have time to go through it directly, so maybe we'll pick that up next time, and maybe we'll have a little short, but go ahead and stop here, I guess. Yeah. So what we've set up now, so we've set up for the insertion case. So insert into the class. So what we're going to do next, what we're going to do next is fix insertion. So when you do the actual insert the node, you just treat it like you're doing a binary search, and then you have to go fix where you inserted it at. So you insert it and then fix it up. So similar to what we were doing with the other one, we were inserting and then adjusting the height. Same concept, just different way to do it. So yeah, that'll be. Nah, let's not. I'm going to go ahead and finish it. So yeah, let's finish this. So we'll just go. We may go a little long actually, but I think I'd rather stop after insertion. So let's do this. So while node.parent color is node color red. All right. So all the parent's color is red. So here we have to keep fixing the can insert a red node to a red node, and that's what we're fixing. So we need to grandparent. So grandparent equals find grandparent of the node if grandparent is null, break. So that one's easy. So if there is no grandparent, we are done. We don't need to actually adjust. So we'll figure out why we don't need to adjust a little bit later, but I'll tell you what it is we're going to set the root node to red or black. So in this case, the root node's red, the new node we inserted is red, and at the very end, we'll go ahead and insert it. At the very end, after our while loop, we will do root dot color equals node color dot black, and root can be null here, so we'll check that, but it's not going to make it through as null at this point. The compiler doesn't know that though. throw new invalid operation. Root node should not be null. And there. So the compiler doesn't know it, but at the very end, we're going to set that. So that's why this case is fine. So if the grandparent's null, we're done. So that's the first case. So otherwise, now we have to start considering the either side of the tree. So if node.parent equals grandparent.left. So what this is doing, it's saying if we're on the grandparent's left branch, then our uncle equals grandparent.right. So this is the other branch, so left and right. So whichever side you're on, we're doing this to the other side. So if uncle dot color equals node color dot red. Now then we need to make an adjustment. So node dot parent dot color equals node color dot black. So we set their parent to black. Then we set the uncle to black so that they match. Black. And then grandparent dot color equals node color dot red. Node equals grandparent. So there we set the grandparent to red, and we'll down here if the grandparent just happened to be root, we'll fix the root as well, and then we'll have black, red. So the else condition here, let's do else. So else, let's see. If the node equals node dot parent dot right. So in this case, we'll need to rotate. So equals node dot parent. Rotate. This will be rotate left. Node dot parent. So at this point, we've got a parent. So we've inserted. We've done some work here. We've figured out we have a grandparent. So we have the grandparent. We've got the parent as well. So I'm going to suppress this. Color equals node color dot black. Grandparent color equals node color dot red. Now we need to do the rotate. We would want to do right on the grandparent. Okay, and I think that should get this case taken care of. We need to do the other side though. So else. So else the uncle is, or else we're on the right side, so we need to do the uncle on the left side. And everything's basically flipped. So we'll just do uncle equals grandparent dot left. If node equals node dot parent dot left. A minute, I'm about to get mixed up. We're missing this section. We'll just copy and paste. Copy and paste. So this will be easy to make a mistake. So let's make sure we don't. Here, this is still good. You make the parents the same and both black. Grandparents red. We set the node to do grandparent. Else here, this one's left. And now we need to rotate right. We rotate left. I think that'll get us what we're after. So yeah, I believe that's what we want. So now I have a test case, I think. Let's see. Yeah, let's do this test case. So let's set this. So we need to set our visualizer to the red black tree visualizer. And let's run it and let's see what happens. All right. So we want to insert 10. So it's easy enough. It didn't color it great. Right, it should have colored it right. Insert 5. Yeah, we're not coloring. Let's see why that is. Is this one right? No, it's this one. Isn't it coloring? Oh. Easy enough to forget. I forgot to remove the values. So now we're using our toString now. So 10, there we go. Insert a 5. Insert a 15. So far, so good. Insert a 1. So there, we had to change these. So notice they all got flipped. Now we insert a 7, something over on that side. There, everything's okay. Now if we insert, well, actually I stopped there. So yeah. So, and then I guess we could print the tree if we wanted. We can see if it's in order. Looks like it's in order to me. Maybe we don't care about the numbers if we're in order actually. So it's our rotations seem to be working. So we're at least inserting correctly. So maybe we'll stop there since we're actually out right on time. So yeah, I'm glad we covered that at least. So there, so we do the rotations just like before. And we have to keep the properties in line. So from here we had, these were both red. Here we set one down, we had to flip both parents. We also flipped the grandparent and we made it red, but then that very last check, we changed it back to black. That keeps us roughly in line, and we might try to make a bigger example and see how that it can get a little out of the perfect tree, but it doesn't get a lot out of the perfect tree. So if we add a I don't know, let's add a 6. There. It added the 6 here, just like we wanted it to. And it had to flip these two, so these both became black. This one became red. But the property's still fine because this one's, it's not a direct descendant, so still fine. If we add let's add an 8. So there. What if we add a 9? We had to do a rotation. So there we go. We finally got an actual rotation. And now it looks a whole lot more balanced again. So here it's starting to look a little unbalanced. Here it's back to balanced. And that's sort of what's happening. So here we would have a slightly worse case than if we'd been in an AVL tree. An AVL tree would have been a little more balanced there. So it might have been a little worse if you picked a 6 or an 8. Here we're back into the same state. So AVL tree versus this one in this state is going to be basically the same for a search. That's what red black tree, it keeps it sort of in bounds, but not exactly in bounds. It's close, but not completely. And in doing that, we trade off some performance, so there's less work on the insert. So there was a lot of things that happened here on insert, This fixed insert looks like it does a lot, but really what's happening, you find the grandparent, and this is happening while it's read. So if it's not read, so if your parent's not read, we are done. So if the parent's not read, we just set the root to black and we're done. If the parent's read, though, then we have to do a little bit of work with find the grandparent. If the grandparents know, we're done. So just good. If not, then if the grandparents, if we're on the left side, we have to make an adjustment to the right side. And what we're doing, we're making both of them black to make sure they're not both red at the same time. So that's really what's happening. We have to do that on vice versa. So it's one or the other, but it's not a lot, relatively speaking. AVL tree insert actually ends up being more complex. There's more to worry about. And that's where we're gaining error value. So next time we'll look into I guess we'll start in I guess we should start in search first, but search and delete. Search may look very similar to this. Delete's going to be a little different, so we'll see. But we'll stop there. Yeah, actually, search I think will be exactly like this actually. But we'll stop there. We'll do those next time. So we'll call it with this one. So this has been Introduction to Red Black Tree. So thanks for watching and have a wonderful rest of your day.